Hi, my name is Faraz Mustafayapur, and I am in the Nevada Extreme Conditions Lab, better known as NEXCEL, under the supervision of Dr. Salamat and Dr. Lawler. And today I'll be going over the poster presentation titled In Situ Raman Spectroscopy on a Novel Room Temperature Superconductor, Carbonaceous Sulfur Hydride, under low pressure and cryogenic temperatures. And before I get started, I wanted to go through a brief overview and structure of how today's presentation will go. We'll start with an introduction and background leading into the motivations and on why we actually want to study these kind of materials, what our research questions and our objectives are, the experimental design and methodology of how we go about doing those and getting our results, the conclusions and our outlook, the acknowledgement and references, and hopefully some questions at the end. And starting off with the introduction and background, one of the most interesting applications and outturns of quantum mechanics is superconductivity, which describes a remarkable set of physical properties, such as having zero electrical resistance and excelling all external magnetic fields. However, the onset of superconductivity in materials historically has only occurred at low temperatures, and as a result, has really limited the industries from utilizing its incredible properties. And if they were actually utilized, they're accompanied with expensive cooling devices to keep the superconducting temperature down. In 2020, however, the world's first room temperature superconductor was discovered and validified as carbonaceous sulfur hydride with a transition temperature of 288 Kelvin or 16 degrees Celsius. However, the current understanding about the material's structural and stoichiometry details, such as the exact ratio of carbon to sulfur to hydrogen atom, is missing, whereas theoretical models fell short in providing more details due to limitations in considering the quantum behavior of hydrogen, while experimental probing methods such as XRD fail due to weak interactions of X-rays with H atoms. Moving on to Raman spectroscopy. Raman spectroscopy is a type of spectroscopy based off the fundamentals of Raman scattering, when light of a certain energy is incident on a material and bounces back with a change in energy. The change in energy is attributed to lattice vibrations and interactions with the lattice vibrations. Raman spectroscopy, however, is a non-destructive physical and chemical analysis technique that gives important details about the chemical structure, polymorphy and phase, and crystallinity of materials. With that being said, we're going to lead into the motivations on why we actually want to study and why researching superconductivity is important. And first and foremost is energy transmission and distribution will be heavily impacted with these kind of improvements. When electricity is transferred from point A to point B and is sent across the grid, there are losses of energy due to wire resistances. And in 2019, the electric power industry revenued $400 billion, in which 5 to 10% of that was lost energy or lost energy due to heat to the environment, which amounts to $30 billion a year. The Department of Energy also reports that the current electricity grid will be oversaturated by 2030, and the power grid has never faced a challenge so great or so critical for our future productivity, quality of life, and economic growth. Secondly, are medical imaging devices. Medical imaging devices are devices that use very powerful magnets to operate, and many of these are supported through superconductors. A paper published in the Journal of Radiology reports that the cost of operation for each MRI machine is $25,000 a year annually, and 50% of that cost alone comes from cooling requirements and expensive devices to try to keep these superconducting magnets below the critical temperature. Whereas if we are able to have a higher and operational ambient temperature with our superconductors, the expensive cooling devices would be obsolete and the technology would be proliferated and expanded into underserved and impoverished communities. And finally, the improvement of superconducting technology will notably impact quantum information science and computing. The quantum bit is fundamentally based on a superconducting phenomena of the Josephson junction. It's a new computing paradigm. Quantum information processing enables a exponential acceleration of computing speeds and reduction in energy cost requirements by orders of magnitude, in contrast to classical computing, which faces energy resource limits and maximum computing powers. And with that being said, we're going to lead to the research questions and our objectives. First and foremost is, what is the Raman spectral profile of CSH under these various temperatures and pressures? What details do these Raman measurements give us about the stoichiometry of the system? And what are the details about the crystal structure? Studying CSH's Raman spectra through low temperature and pressure space will provide a huge understanding of the material's phase diagram. And for this kind of data collection, a system needs to be built capable of actually measuring these spectra at these various temperature and pressure conditions. With that being said, the experimental design has several experimental factors to be considered, and first and foremost is temperature. In our group, we use a liquid helium-cooled cryostat to actually achieve temperatures comparable to that of space, which consists of a vacuum vessel as an insulator between the outside environment and the sample inside, and a pumps liquid helium through a compressor to the cold head to actually achieve those low temperatures. Second is pressure. So to achieve high pressures, our group uses diamond anvil cells, which is 2 diamonds placed on top of each other with their faces facing each other and a sample between them. The diamonds press and squeeze onto each other, and they induce a pressure on the sample. And this uses the optical and mechanical properties of diamond being the hardest material found in nature and transparent in a variety of wavelengths. And finally are the optics of the system, which we've used a clever way of actually imaging within the cryostat, which historically hasn't been done before, which is explained in the next slide. But however, in this picture, we have the laser lasing from here, the solid state laser going through the system, getting to the sample through the correcting lens, which I'll explain in the next slide, through the sample within the cryostat and going back to the system of the laser cleanup system, the imaging system, and the spectrometer itself to actually get the Raman data. The optics of the system is a clever way of actually imaging because historically, placing objectives close to the cryostat was difficult because of all the obstacles that the cryostat created with its housing head and its legs and being bulky on an optics table. So our solution was actually integrating an imaging lens within the cryostat, which is mounted onto the DAC, which sends the image outside of the cryostat, which gives us more working space to actually place more optics, and is collected with the correcting lens and sent back to the system. And you can see a diagram of our system here below with the laser going through the correcting lens to the DAC and back through the system. With that being said, at the current time of recording this video, our CSH samples right now are at the APS synchrotron in Chicago, undergoing XRD measurements. So as a result, in a proof of concept and principle, we tested our design on methyl ammonium lead iodide and imaged H3S within the cryostat. So these are actually images within the cryostat. We can see the diffraction delimited images where we can see the indentations on the gasket, the diamond, and actually the sample here. And on the right, we can actually see the lower wave number Raman spectra of methyl ammonium lead iodide as a function of increasing temperature. Whereas these low temperatures, we see narrow peaks and no thermal noise. And with increasing temperatures, we have a broadening of the peaks due to thermal vibrations and thermal noises as a function of increasing temperature. And with that being said, are the conclusions and our outlook for the future are that we hope to get the material CSH from our colleagues at the APS right now and load it into our cryostat system and actually collect the data in various pressures and temperatures. And we actually hope that this research will help future researchers reduce the pressure requirements for CSH to actually make the technology applicable in industry and proliferate those industries that we discussed previously. And so below, we actually see CSH loaded into our DAC. And so these metallic shiny pieces you see here are the CSH material at the XRD Advanced Photon Source at our National Lab in Chicago right now. And with that being said, I wanted to go through and thank Dr. Salamat and the Nexcel group for all their help, support, and input on the project, and UNLV's Physics Department's Research Design Engineer, Paul Ellison, for his patience, guidance, and aid during the fabrication experimental design. I would also like to thank the NIH Nevada Inebriate URP program for actually funding and giving us the grant possible to actually go through with this project. And with that being said, I'm looking forward to your questions below and being able to answer any questions you guys might have about this project. Thank you.